All right, so here we are at probably the biggest application of finding derivatives. So here we go. We bring our understanding of finding derivatives into finding maximum and minimum values of a function, of any given function. So let's get started into it. So now, even though we will ultimately get into that idea of how we can bring our derivative understanding into finding maximum and minimum values of a function, of any function, but really allow me to build a really strong foundation for anyone before we really get into this finding maximum and minimum. So it might take me a little while in this video lesson to get that, to build up that strong foundation for anyone viewing my video, and then once everything is being in place, then this real work of finding maximum and minimum values on any function will come out a lot easier. Okay, so now, just like usual, I am going to have to erase away this title of our discussion here. And let's now look into a quick little function. And for anyone looking at this function, this graph here, you don't have to worry about what function it came out from. It's just basically, at this point in your understanding, a graph as long as it's passed the vertical line test. So quickly sum like this. As long as you have a graph that at every value x, vertical line test, say as long as our x value there pass through the graph only and no more than 1 point on the y-axis, then that's what it means by passing the vertical line test. But passing the vertical line test for any graph means that this graph here came out from a function. Okay, and so that's why, back to what I was saying earlier, as at this point, as long as your graph passed a vertical line test, then we know for sure that the graph came out from a function. And so let me now quickly bring up an example of a graph that already passed a vertical line test. And then all right, so here's on my computer screen, and here we go. So I don't need anybody to worry about what function this graph is, but obviously this graph here has passed the vertical line test, and you can quickly pause the video or take a moment to verify that for yourself. So obviously this graph here came out from a function, some kind of function, and like I said again, I don't need anybody to really know what function that is. Is that an x to the fifth, is a polynomial, or the whatsoever that is? We don't have to know about that. What I want everybody to understand now is that this function, and combined together with some of our past understanding in terms of the function is going up and down, then yes, back to what I said earlier, anytime we are looking at a graph, then we must be viewing a graph from the left to the right. And so now allow me to introduce let's say I'm going to put a point on the graph. Okay, and so this point here, as I'm trying to drag the point along the graph here on the graph from the left to the right, so that's always a permanent convention that anytime we're viewing a graph, we're going to put the graph from the left to the right. So from the left to the right, then you can see that my black point here on the graph is doing a lot of going up and down and going up right there. Okay, so let's start it over again. Let's go back from the beginning point again. But wherever my point here that I decide to be the beginning point, then see, it has, as I'm keep moving from the left to the right, and it going up, and then it swing it way down, and then swing it way down enough, and then it swing it way back up again, and keep doing that. And so this graph is doing quite a couple turning points here. So now I'm pointing out that nature right here, so that everybody can understand that any graph, anytime we're looking at a graph, then we must expect that the graph has quite a few places where we call the turning points. And turning point here, I mean it turns in a sense that it was going up in vertical value, and now I'm being clear about up and downs means the vertical values. And so turn points now means those places. And of course, here it's just a brief introduction right now, so I don't need anybody to be exactly worried about where exactly those turning points are yet. We will get to any of those. But so just want anyone to realize that there are a couple places here, like say right here we got a turning point where we turn from going up and back to going down. And then we go, the point here travel and keep traveling along the graph and going down enough, and to a certain point it's going to start turning its way up again. Okay, and then keep doing that way. The graph, that point there is making its journey to hit another peak. And so now I'm starting to use another term here. It's a peak. So there's a peak. We hit to a high peak here, and then we hits down to a low peak, and we turn our way up again. And then here we hit to another peak, and we turn our way down, and hits to another sort of like bottom peak, and hit up. Okay. So enough of that turning back and turning up and down on the graph. But what I want you to understand is that, so it's just the way how any function is. It got up and down, and it got up and down. And so because of that way, you know, there has to be those turning points where it's going up and then it make its way down, or it's heading down and then it makes its way up right here. So we will learn and we will find out how derivatives are going to be playing an essential role in helping us to detect all of those turning points. Okay, and so now let me now get back to that computer screen right there. Okay. So here we are, but this time allow me to put the computer screen together with where I stand right now. But so let me now, together with that point, that moving point I was describing earlier. Okay, so now we have a moving point, and always keep rule of thumb, we keep that moving point to be moving from the left to the right. Okay, because as we moving that point on the left to the right, from the left to the right on the graph, then we will observe those of up and down vertically on the graph. Okay. So now this is what I'm doing. So we're still pretending that we're having that point moving, but we want to put on that tangent line. Okay, so there you go. Now let me put that in really some close zoom. So now here's the graph. Okay, and so now the black little line here doesn't have to be long, doesn't have to be the entire line, but right there what I'm indicating here is we have, let's say anywhere I put my point on the graph, we have a tangent line. Okay, and so tangent line, it's just that concept we have been learning all over the quarter up to this point. And so now let's say when I'm at somewhere here, at some instance here on the graph, then my tangent line, if I placed a tangent line right here, then from the left to the right, this tangent line in black is a tangent line that's rising. Okay, and then, and here of course I really don't need any viewer to be too worried about any fancy terminologies or anything like that. It just use your own eyes to make judgment that anywhere that it seems like there's an interval, it seems like there's a whole area, there's a whole zone of values on the x-axis where my tangent line remains. Of course it changes value, but it still remains going up, rising. And then as I keep moving my points from the left to the right, you can see that there will be a certain, when we hit to that where I so-called the turning point, the first turning point here, that the tangent line seems to be flat out. Okay, and flat out is just a common daily term, but really what I mean now is that the tangent line will instantaneously hit a horizontal tangent line. It will become horizontal instantaneously. But then immediately as I move to a next point, then the tangent line is start turning down right here. Okay, so now as I'm moving my point along the graph, now then you can see that the tangent line remain pointing down for a little while, and then as we hit to that bottom peak where the point is starting to make its way up, then tangent line is going to become flat out one more time, but only as a small instant, only instantaneously, because oops, right there, as I move on to the next point, keep moving further to the right hand side, then the tangent line is making its way pointing back up again, and remains pointing up until I reach to the next turning point. Okay, and so tangent line, ladies and gentlemen, tangent line is the best way. Using a tangent line is the best way to detect where those turning points are all about. Okay, and so now let me get on the other board there. So just like how I was saying now, then it's time that I'm going to introduce a couple terminologies. So I'm gonna create a different graph. Doesn't have to be exactly like the one you saw on the computer screen earlier, but it has enough up and down so that we can understand a few things. So my graph here, my hand sketch version here is how about a graph that's going up, hit its way, and then turn back down, and then turn up, and then turn down. Okay, and of course, I'm not going to restrict that. It could be keep extending further. But now, see, if at any point, just like how I was pointing out on that quick little graphical animation, and at any point here about, and when I say here right now, you don't need to worry about where exactly is here, just kind of like somewhere in this zone here, then we're going to have positive tangent line all over. See, so anywhere about this starting piece right here, then we have positive tangent line. My red little line right here is a tangent. And then there will be a point, and of course, there's still no way we can find the exact yet. I have not gotten into that point where we can find the exact turning point, but let's say about there, graphically speaking, then our tangent line, our tangent will become flat out. Okay, so just like that, then now when it navigates down to the point is getting down to, I should have used red ink. So when the point turned to somewhere to the right hand side of that turning point, then once again we obtained, just like how we saw in the computer animation, and we got tangent line being pointing down. And so that turning point there, of course, any point on the graph, any point on the plane has an x and y coordinates. And so, of course, the y values are the vertical height on the graph. But let's say we hit, now I'm saying that we hit a turning point. Our first turning point on this graph, at least within what we see here. At, how about this is some value x equals a right there. Okay, and then we could continue just like how I was doing that animation. Then we continue moving our point to further values on the x-axis here to the right hand side. So it looks like we hit another turning point at this bottom peak right here. Okay, and so about there that's where x reached to another value, x equals b. So, and like I said again, strictly we stay in that rule of thumb that we have to be moving our points on the left, from the left to the right. And then along with that way, we're going to be able to observe all that fascinating up and down right here. And so now I'm going to extend my x-axis, my horizontal axis, a little further. Okay, and so about when we hit to this other value right here, this third value, how about x equals c right here, then it seems like we hit another, our tangent line becomes a flat out again. Okay, so now, graphically speaking, visually looking at it, a lot of ways how you can say about it, but in the end, at those turning points, now formally we refer to those as, see these x values, I'm talking about the x values where it caused the turning points. These are now, we refer to these as the critical, okay, the critical values. Right, so far according to this picture over here, then I can see that I have about 3 critical values. So critical values right here from this hand sketch version of mine, those are the x values. Critical values are the x values where our function hits horizontal tangent line. Or so now let me put that into a more mathematical approach right here. Horizontal tangent line, it's just a graphical description. But horizontal tangent line means the slope of this tangent line is 0. The slope of that tangent line is 0. And the slope of this tangent line at that point, x equals c, is also 0. So one thing being in common about throughout all these 3 different critical values is that the slope of the tangent line there hits 0. So that means right here, slope of the tangent line is, in what we understand so far, the derivative, okay, the derivative at that value. And so that means f prime at a, for sure I know it's equal to 0, because our tangent line becomes flat out, or our tangent line becomes a horizontal tangent line. And so the same way right here, I know for sure that right here at that point, my f prime at b, my slope of the tangent line at x equals b has to be equal 0. Okay, and the same with this other turning point here. Okay, so the point on the graph itself, I call that the turning point, but now the x values where we receive those turning points again, then we call them the critical values. Okay, so f prime at c here also equals 0. All right. So this is not all what it means to be critical values. There's a little more than that, but at least this is the more important part of what it means by being a critical value. Okay, so now we are ready for an actual formal definition of what it means by being a critical value. All right, so I'm heading back to my earlier board, my other board. So now we're gonna come to a definition. And so now as a formal definition, okay, and so it's my shorthand writing for definition. But so a function, okay, a function f of x is said to have a, and now let me switch to red ink right here. So a function f of x is said to have a critical values, or value. I shouldn't use a plural because I mean when here we just defining one. So a function f of x is said to have a critical value at some value x equals c. Okay, so quickly let me swing back to the other board and see. So if we say that this function has a critical value at this point right here, that means or I'm saying here in our formal definition, if the derivative of the function f prime at c, okay, equals 0. All right, and I'm not done yet with my definition. A function f of x is said to have a critical value. So there's a new terminology for us here, new term for us. It's said to have a critical value at x equals c if f prime at c equals 0. Okay, so let's find out if that definition is consistent with how we saw that in the picture. And yes, that is. See, it looks like right here in this graph, I already saw three turning points. And so I call the x values these three different places on the x-axis where it caused our graph to turn, right? Then I call those the critical values. So what happened there at the critical values there? The tangent line was, the slope of the tangent line was 0, the slope of the tangent line was 0, and the slope of the tangent line was 0. So yes, this definition is consistent with the explanation we have seen earlier through the graphs. But this is not all that is for being a critical value actually. So a function f of x is said to have a critical value at x equals c if f prime of c equals 0. Or, this is another condition, but watch out, it's an or, so only one of these requirements will pass for your point being a critical value on the x-axis. Or f prime at c is undefined. Okay, and being undefined here means we don't have a slope of the tangent line at that point, and that's what it means by being f prime at c is undefined. Okay, and so this case right here is, I mean, we don't see it as often, but it does happen out there. So let me quickly swing to the other board and explain what it means by having a, let me erase some small portion of this graph. So I explained a little when it was earlier in the quarter. I already explained that there will be times where your graph create a sharp angle turn. Like say, for example, I could have made my graph like this. Okay, so it was going up, okay, and then all of a sudden it's created an angle, a sharp angle, and turned away. So a place like that is where, okay, we have an undefined, or that derivative fails to exist. So right here, you can say that f prime at c, right? One way you can say is undefined, okay? Or another way you can say, okay, fails to exist. I mean, fail to exist if we are looking at that derivative as the concept of a limit, or we can just say that, hey, the f prime there is undefined because we don't even know what that we don't even know what that slope of the tangent line is when it really hits x equals c on the x-axis. Okay, and so this is also another critical value right there. So on the x-axis, x equals c caused an undefined slope of the tangent line, and so that's why we also classify that as a critical value as well. Okay, and so that's now a clear definition of what it means by being a critical value, right, of a function like that. And so now let me really bring up an example to get my viewers, to get my students who study with me really comfortable with how we can find critical values, because just with this definition we can already have a good amount of good problems for us to detect where the turning points are, okay, and where all the critical values are. And in the end, being either having an undefined slope of the tangent line or having a horizontal tangent line right there, it's all about at those critical values our function is turning its direction. See, these are the critical values where we have horizontal or flat out tangent lines. But right here we have an undefined slope of tangent line. But in any way, it's all about those are the critical values where our graphically speaking, our tangent lines or our graph is turning its direction. So one way and direction. What do I mean by direction? You see, as we keep moving on from the left to the right, the function was rising. That's one way, okay, and then falling down. That's why it turned direction. There was that small instance where it hits zero, flat out for tangent line, and changed direction. And then it keeps hitting down to a certain bottom, and then it hits to a bottom low enough, which is the way how the function is, low enough that it's going to turn the direction and heads its way up again, and then heads its way up to that sharp angle, and then turn its way down the whole, and turn its way down, and really it's not always going to have to be down actually. And even when I'm talking about, I got to be a little more specific here, but turning direction, it could still be going up. It could still be going up, but it's turning it's sort of like turning in a different ways right there. You see what I'm saying? So it's still a different direction where the graph is heading right there. Okay, and that's the whole idea about where I call these critical values in a graphical understanding. It's a place on the x-axis where the graph is changing its direction right there. Okay, and so now I am going to take about a minute or so to erase the board, and we're going to fire up some good examples. All right, so now here we are at example 1. So in this entire example 1, the main instruction of this example is I just want to find, okay, let's just find the critical values. I mean, find a critical value or all of the critical values, right, of and so now after that main instruction, now I'm going to give different functions. So how about our first function here is f of x to equal x to x cubed minus 3x squared plus 12x plus 1. All right, so here we go. We have a function. And so now I want to find the critical value. So it could be 1 or it could be 2. It could be a lot. Okay. So, but we want to, there's a way for us to find all of them. So just straight out from that definition we've learned, the critical value, any value on the x-axis, if you want to call that the critical value, it has to satisfy either f prime of c equals 0 or f prime at c is undefined. So as long as we can detect those values x equals c on the x-axis, where it only need to meet one of the two requirements here, then we can call that those are our critical values. Okay, there could be one, there could be many. Okay, so at this point I haven't gotten started into the math, so there's no way I can tell, but let's do the math formally. But you see, straight out in the definition, it needs a derivative. It needs derivatives. It's the key, the essential step here is to find the derivative. Okay, and so now now I'm realizing that I need to first take the derivative, and this is where all that skills you've been learning throughout all those times prior to arriving at this video help. Okay, so for taking the derivative here, so this is not our first lesson in how to find derivative, so I'm not gonna go slow on taking the derivative here anymore. First term gives me a 6x squared due to the power rule. Second term here is minus 6x. This third term is a plus 12, and the constant term is gone. Okay, and so now this is our derivative of f, or in other words, it's f prime of x. So what we need to do next is, recall again. The critical value, any critical value is the place where it's f prime at c equals 0, or f prime at c is undefined. Okay, I might have to keep repeating this a lot to trigger your understanding, but you see, so right here our derivative itself, have a good observation. Of course, allow me to bring this term back at this point of your learning, but in the end the function we have here was a polynomial, and now after we take the derivative, its derivative is also a polynomial. So for any polynomial, there is no such thing as a value that's making this polynomial undefined. So I'm not going to have to worry. So that's my argument right there. So in this case, I can already rule out that scenario where our derivative being undefined. So that means this doesn't need to be concerned here. Doesn't need to be part of our concerns, because we already knew that any polynomial won't have any undefined points. A polynomial is defined everywhere. So that means the only challenge left for us is we got to find out all the values of c, or the x values that gives us 0 derivatives, or we have to find all the values c right there, satisfying f prime at c equals 0. Think for a moment. What work will that bring us to? That work there means I need space, so I'm going to have to erase this. But all that is now is to say that we're going to just simply set our derivative f prime 6x squared minus 6x plus 12 to equal 0. Okay, we just simply have to set our derivative equal to 0. And what's the point of doing all this? We will, after we equate our derivative with 0, we are going to solve that equation here for x. Okay, so the big calculus step is here. We find the derivative, but once we've got the derivative, we got to go back to the algebra and be able to solve an equation like this for x. And so at this point, I can leave that for my viewers, for my students, to take your own choice, your own preferred method to solve for this equation right here, because the way how I see this equation here is only a quadratic equation, which is very familiar for anyone who is studying calculus. Okay, so I just need to briefly remind that the most common method is to apply the quadratic formula. Okay, but it might take a little bit of calculation because we need to pull out a calculator and plug it in. The second to the most common method is to find the factoring. Okay, factor out, which is what I'm about to do here, because this is easy enough for me to factor. So I am going to factor this. And then the least favorite method is to complete the square, which is, I'll just mention, but I doubt if anyone is gonna follow with that path like that. But you always have three methods to solve like that. So with this one right here, I can see that I have a common factor 6 throughout all three terms. So it's 6 factored out. Okay, and then there's x squared minus x plus 2 equals 0. Okay, and now as I said, even though, so you're not, you don't have to follow this way of how I'm solving it. It's just my choice right here. So 6, and now I'm going to factor this, x squared minus x plus 2 into x minus 2 times x Okay, and I apologize for this, but there is actually something I have to fix here. It was a typo that it was a little writing typo that I incorrectly write it down from my lecture notes right there. But this sign right here, previously it was plus, but it was meant to be minus. Because otherwise with the plus, then we couldn't proceed on with the solving equation here. So all those signs here will all be negative. Okay, and so when it came down to this, it would be factor out the x squared minus x minus 2. And then here we're looking at the two factors here, x minus 2 and x plus 1. All that there equals 0. Okay, and so now at this point here, clearly we are looking at two different solutions. X equals 2 and x equals negative 1. So thinking strictly in terms of solving a quadratic equation, then these are our solutions. These are the solutions that give me a 0. I mean, when we substitute these values into our quadratic, and it gives us that quadratic on the left-hand side equals 0. But now in this particular context, in this particular situation, these are the values where it gives us 0 value derivatives. So 0 value derivative happens at these x values. So that means we have found our goal. These are our critical values. We have found two critical values. And so the solving work, the big generality here is that once you have found your derivative, then just simply set or equate your derivative with 0. So, and from there we're gonna, it could be here it's a quadratic, it could be something else, but basically we have to solve that equation after we set our derivative to equal 0, and we solve that equation for x. And once we have successfully solved the equation for x, then all of these, after our solving work, provided your solving work, that's why it takes the algebra right there, okay? But provided that your solving work algebraically is correct, then these are all your critical values that this function will ever have, okay? And so now we found the critical values of a function of ours right here, our first function in our example 1. So now let me look into another one. All right, so I am going to look at part B of our example. So how about in this example, I'm looking at g of x to equal cube root of x. So once again, to find the critical values, or to be able to find all critical values, we have to first start out by taking the derivative of our function. So back to the original function itself, remember that same trick we've been doing all over the quarter here. Any roots, square root, cube root, fifth root, fourth root, any root is being regarded as a power. So here cube root is a power 1/3. Okay, and so in that way our g prime now is going to be 1/3 times x to the minus 2/3 power. Okay, and to keep things clear about this, then this final expression here can be rewritten as 1 over, it's a cube root of x squared. Yeah. Okay, so if the problem here simply is a derivative problem, finding the derivative problem, then we would be good right here. But now because we are using derivative for the next step, and so I'm introducing this work right here. Okay, and so now we're gonna set our, okay, so we're gonna set our g prime of x to equal 0, and then after doing that, we're gonna solve for that equation. We're gonna solve that equation for 0. So here we go. That means we have 1 over cube root of 1 over cube root of x squared is to equal 0. Okay, and so this equation right here, so this equation right here has a no solution. Okay, it has no solution because, so here, think about it this way here. So first of all, if we're picking a value, think about, here's how I defend this answer right here. If we're picking a value x greater than 0, positive x value, then when substituting that inside of our left hand side here, we are going to have 1 over cube root of x squared has to be completely a positive value, and positive value means strictly above 0. It cannot equal to 0. Okay, so you can quickly test out what I meant right there. Here I'm using a general proof right there. If x is a positive value strictly above 0, then substituting in, because due to that square right there, taking the square in, see that square inside the cube root here, so square of any value is going to make it positive. Okay, so cube root of a positive number is a positive, so 1 over that positive turns out to be positive. You can quickly verify me by doing this. 1 over cube root of, how about, 2 square. Okay, you can quickly do that calculation, and the answer, all I care is it above 0 or not, and it will be. Okay, and so it's just a quick way for viewers to verify me like that. And so back to what I was in the middle of saying, if x greater than 0, if x is greater than 0, if we picked a value for x greater than 0, then this left hand side is strictly positive. Greater than 0, greater than 0, the value output from this expression. So we can achieve the left hand side equals 0 for any value of x greater than 0. So that's one thing I ruled out already. So I ruled out that we can't have, so in order to have this, we can't have a solution being positive. Okay, so what about in the entire real numbers, the entire line of real numbers right here? X greater than 0 is not the only way, it's not the only choice. So what about when x is less than 0, when x is a negative value? So when x is less than 0, then here's what happens. If x is less than 0 or being negative, the expression on the left hand side here, 1 over cube root of x squared, is also positives. Okay, and I hope it's not a shock to anyone, but once again, here's how it happens. Because recall for yourself again, inside of this cube root we have a square, and so if we're substituting in a negative value, even though x is the x value that we're substituting in being a negative value here. Think about 1 over cube root, but substituting in with a negative 1, for example. Negative, and see, I use parentheses very carefully right here. So squaring, due to that square, it will always force, even though with negative number, it will always force the value into a positive. And so cube root of an overall positive value once again turns out positive. And you can quickly verify me on this. Okay? And so generality, as a generality, even if we pick a negative x value, this left-hand side is still above 0, will not equal 0. Okay? There's one value I left out. So what about when x is equal to 0? Okay? Recall from your algebra, if x is equal to 0, look at your, if we're looking at our g prime of x here as a function, then the g prime is not even defined. So g prime of x, right, is undefined. And that's what the definition here, that this is a point where it hits to our definition. When we pick an x value greater than 0, this equation is not satisfied. When we hit an x negative, this equation has no solution, has no satisfying value. And even if when we hit an x equals 0, our g prime becomes undefined. That means in the end the equation still has no solution. But we can take some advantage right in this line right here. If x equals 0, our g prime of x is undefined. Okay? So that rings a bell for us. That even though this equation to solve here has completely no solution, but at the end, in the end we still found a critical value. That critical value is where we have our g prime right here being undefined. Okay? And so now here's my conclusion. So because g prime, right? So because g prime is undefined, okay, at x equals 0, just the way it is. So I purposely solve for that for you to understand that sometimes taking the solving work is always a standard, even if sometimes it might feel like a waste of your time right here, but it's easy to detect where we can have a 0 value or where we can have even an undefined point. And so now we came to the conclusion that g prime is actually undefined at x equals 0. Okay, and so that means as far as critical value, we have x equals 0 being our critical value. Critical value. All right. And now I am again going to erase the board, and we are looking at another problem. Okay, so let me now write down part C right here of our same example. So how about h of x? And our function here was e to the x plus e to the minus x. Okay, e to the x plus e to the minus x. Okay, so this function, again, just to find the critical values, the first standard step gets the derivative. So hopefully after 3 little problems right here, viewers of mine or students who are studying with me are starting to set into a routinely work right here. We've got to find h prime of x, the derivative of the function, because this is where, like I said in the beginning of my video lesson, this is this is probably the biggest application of using derivatives. Okay, So we find h prime of x, and that here derivative of e to the x is e to the x. So first term taking the derivative gives me e to the x. Second term taking the derivative gives me e to the minus x, but chain rule says take the derivative of the inside. So in the end, altogether my derivative here is e to the x. The negative 1 here makes the sign here becomes negative. So subtract e to the minus x. That's the derivative of our function. Now be careful. It's a e to the minus x here versus e to the x. So these two will not cancel. I mean, I've had students in my past time mistakenly canceling out these two due to the fact that they didn't realize there was a negative sign right here. So watch out for that. This is e to the negative x. This is e to the x. Subtraction between them. So still two separate functions. And this is our h of x. Okay. So if this was simply a finding derivative problem, then we would be done right here. But we're going to take this derivative for the next step. So I suggest that we write this expression as e to the x minus 1 over e to the x right here, because that e to the negative x is exactly the same algebraically as 1 over e to the x. Okay, and so now back on that standard step right there, we are going to set our equation. We're going to set our h prime of x to equal 0, and then we're going to carry on our journey from that point on. We're going to solve that equation for the x values right there. So that means e to the x minus 1 over e to the x. On the left hand side, this is h prime. We're setting that equal to 0, and now we're solving this for x. So this equation here, it takes a little algebra, but we can multiply both sides of this equation here because we have fractions. So I understand there used to be a time I really hate fractions, and that's probably the same with a lot of viewers out there. So what do we do when we hate fractions so much? And we try to find a way to clear out all the fractions, right? Clear the fractions away. So we got a fraction staying right in our way right here. So let's try to find a way to clear it out. And the only way to clear out fractions in an equation is to multiply both sides of the equation by that denominator. Okay? And so that means I'm going to multiply both sides by e to the x. So if I multiply e to the x to both sides, the left-hand side, we're going to need to multiply e to the x for two terms right here. So that means first term becomes e to the, maybe I shouldn't rush right here. I shouldn't rush. Let's multiply e to the x on both sides. Okay. So 0, multiply e to the x on both sides. That's what the plan was. And then now, because of that, now multiplying e to the x to each term right here. Now in my next step, e to the x times e to the x is now going to become e to the 2x. Okay, that's what the first term is after distributing that e to the x. The e to the x now multiplying with 1 over e to the x will cancel out with that e to the x and gives me 1 right there. Okay, and all that equals 0, because e to the x times 0 is a 0. Okay, and so now I need the next board space. So I'm going to take a minute or so to erase my board, and then we're going to swing over to the other board. Okay, so now continuing from where we were, e to the 2x minus 1 equals 0. Now we can just add 1 from both sides right here. I mean adding 1 to both sides. So e to the 2x equals 1, and that's what we can produce. And so now just here is just a standard algebra technique to solve for exponential equation. I'm going to take the logarithm, the natural log, to be the best right here. Take the natural log on both sides right here. So here I'm going to produce so natural log of e to the 2x, okay, equals natural log of 1. And so right hand side gives me a 0. Left hand side, the natural log of e to the 2x gives me simply just 2x. And so I highly recommend, again, you got to review your algebra in order to understand all of these steps right here, because I'm using just all the elementary algebra, nothing fancy about these. But if your algebra is kind of faded away, then make sure you review that Or if you're a student studying with me, then you can find a way to get a hold of me right there. Okay, so then we're dividing both sides by 2. Then now clearly our equation here turns out x equals 0. Okay, so we were successful finding an equation, finding a solution to this beginning equation of ours. So recall that our beginning equation was, see, e to the x minus 1 over e to the x to equal 0. And then here was part of my work there. Okay, so that was the beginning work. Okay, and so now in that way, what have we found for ourselves? So the question in the beginning, we wanted to find critical values. So what we came up to now is that x here is our critical value over here, because this x value gives me 0 value for my h prime right there. So this e to the x minus 1 over x will equal 0 when x equals 0. So that means, so now as far as the critical value we found, and this is the only one, and we don't have any undefined value. So as far as critical value, we only have one this time actually, x equals 0. That's our final answer for that. All right. And I will be having another FYT for my viewers or any of my students. And so as far as an FYT, I want you to be able to get your work done independently, and you can pause the video if you need to. So as an FYT, but this is still part of our example 1. So find the critical values, but what I give you now is a function f of x equals, so how about 1/3 x cubed plus, minus. I learned from that mistake earlier about my typo. So minus 5/2 x squared plus 6x. Okay, so go ahead and spend your time finding all the critical values of this function right here. And now I'm going to go ahead and wait until you're back after pausing the video and take your own time with that. All right, so hopefully you're back and having your own time. So just the way how it has been for all of these FYTs that I've been offering, then I'm not going to go through the steps. I'm only going to tell you the final answers. So the critical values we will find is going to be x equals 2, and there's another one, x equals 3. These are the two critical values for this particular function. All right. And so now, once we're done with example 1, and hopefully at this point everyone is thorough with, is really through with all of the, that essential skill of how to find the critical values. Then, now if we're looking back at the graph that we have seen earlier, and still I didn't have to say what function this graph is, but see now those turning points that I was introducing on the graph. The turning point, we have one right here, okay, and we have one right here, and we have one right here, and we also have one right here. So those x-axis right here, x values, so x values, there's an x value right here causing a turning point, there's an x values right here causing a turning point, there's an x value right here. So in the end, at least for this graph I'm seeing here, we should be having 4, what I so-call now informal term, critical values. Okay, so whichever x equals here and whichever x can equal here, we got 4 critical values on our graph. Okay, so now if we're looking back at allow me to stay on the hand sketch version actually of my graph. And I'm going to take another minute or so to erase my other board for a hand sketch. Then in the picture that I was drawing earlier, then we had a function with up and down and up and down. There are lots of up and down and up and down. And so now we already knew that at places like this on the x-axis, let's say I call this x equals a, and at that particular point right here, we call that we have a horizontal tangent line, okay? And so we call this x equals a, this x value on the x-axis, the critical value. But then that means, you see, as a tangent line, and if we place a tangent line anywhere on the interval to the left of a, because now once you clearly, and now you already learned that skill to find all the critical and to detect all the critical values, then once you put all of your critical values on an axis like this, okay, and put it all together in one picture, then see, at the critical values we are having horizontal tangent line. So x equals c here, x equals b here, and we have horizontal tangent line. But that means, what about those intervals? Because outside of those critical values, once you arrange them in increasing order like that, then they split our entire, now I'm using that term, once we place down all of our critical values on the line of numbers, then they will for sure split our entire x-axis into separate zones. How many there are, it all depends on how many critical values you can find. But here, let's say in this quick descriptive picture right here, then if I'm putting up that scenario where we have three critical values, for example, then the entire graph is being split it into 1, 2, 3, and 4 separate zones, or 4 separate intervals. And so in this interval right here, so now let's ignore that critical value, but now only pay attention to those intervals between any of those intervals between the critical value, between any two consecutive critical value. Then say right here in this first interval, then the entire interval, at least this is what commonly happens to any tangent in this entire interval. In this entire interval, any tangent line will be, see, pointing up. From the left to the right, the tangent line is pointing up. It may be pointing up less steep, or maybe pointing up quite steep here, but in the end, tangent line in the picture like this, they're all pointing up. And then that's why these critical values, I call them, they are the turning points, because the tangent lines are pointing up, and then it turns to flat out, and then after that it turns down the opposite way. And so now think about if we place a tangent line anywhere in this interval right here, inside of this interval. If we place a tangent line anywhere there, then the tangent line will have a common look right here, be pointing down. Okay? And then once again, tangent line will remain pointing down until it becomes flat out right here at this turning point. And then after that, it's going to swing back up. It's going to make its way back up. So if I create any tangent line about anywhere here, then there you go. Our tangent line from the left to the right is having a positive slope. And so just like that, again, I'm putting back on screen that graph we've had earlier. Okay, so there you go. Here's our point, our tangent point, our point on the graph. And from the beginning, where it was in the beginning, okay, then this point right here, see, these are our critical values. So we got one right here, we got one right here, we got one right here. See, the machine is good enough, is sensitive enough to kind of quickly detect these values for us. And now you already knew the math to precisely get these values. But see, if these are our critical values right here, then we have some area where the graph is, the tangent line is pointing up, okay? And then up, and it keep pointing up until it hits that flat out, that turning point. And then after that point, it's going to start turning down. It's in this way of the graph right here. So the point now is that those intervals between any interval between any two consecutive critical values, those we have some what so-called increasing and decreasing. Okay, so this is the see how the tangent line is pointing up for here. It's increasing. It's indicating that the graph itself is rising. So positive tangent line, positive tangent line. Now I'm saying that precise term right here, having a positive slope of the tangent line. So slope of tangent line is positive and become flat out, and then turn its way down and become negative slope of tangent line right here, because see the function here is a dropping value. Okay, so back on my hand sketch right there again. Then the slope of the tangent line is positive. Okay, the slope of the tangent line is positive, indicating that the function is rising. It's rising up from the left to the right. So anywhere that we recognize in any interval between any two consecutive critical values, and we recognize that nature, that the function here is having positive, see the derivative of the function, that the tangent line is having positive slope, then our function is increasing. So here I'm calling that the function is increasing, and that's the formal term for that. And increasing means the derivative is positive, okay, greater than 0. And then when we're in an interval like this, for example, obviously from the left to the right, right? Then and it's between our two consecutive critical values, then the function was dropping value. The function itself is dropping value. So that means in this interval here, our f prime, see that slope of the tangent line right there, it's being negative. Okay, f prime is negative, or the formal term for that, our function is decreasing. Okay, we're looking at decreasing right there. Okay, and so now on that interval, in this interval, the tangent line once again is making its way, and it's only in this graph. It's in this graph right now, and the tangent line is pointing up. So f prime must be positive. That's one thing I know for sure. Okay, and then formally we call that it's increasing. Okay, so that's what it means by being, increasing and decreasing. And so increasing and decreasing, it's a property. Those are the two properties that only happen in an interval. It's not going to happen at one single point. One single point makes no sense. Okay, it's increasing or decreasing have to take place over an entire interval. Okay, and so now, so after the graphical description of what it means by being an increasing or decreasing, okay, then let's come up with a generality right here. Okay, so in generally this is what we recognize through the graph right here. But so the function f of x will be or is increasing, and the term here is allow me to actually skip the formal definition of what it means by being increasing. It's just graphically speaking, it's rising from the left to the right, that's increasing. And then from the left to the right, if it's falling, if it's dropping, it's decreasing. So, but now this is what we generally recognize right here. F of x is increasing on an interval from a to b, okay, if the derivative of our function in that interval is how about let me write that piece down here. If the derivative is positive, okay, on the same interval, okay, and so let's see how that generality is being consistent with our work right here. You see, the derivative is being positive. The derivative is being positive in an interval like this. That's where the graph itself looks rising from the left to the right. And then so same way here we recognize right here in this graph there's another interval from B to C, for example. And then in this entire interval over here, then anywhere we place the tangent line, then the slope of the tangent line is positive. The derivative is positive. Okay, and so graphically speaking, the graph from the left to the right is rising. Okay, And so that's how we formulate. That's how we formulate increasing and so now same way, generally f of x, the function is decreasing. And I only explain what it means by being decreasing through the graph right here, rising or falling, but without giving a formal definition. But hopefully you already had an understanding of what it was right there. So f of x is decreasing on an interval from a to b right here. If the derivative, throughout what we have investigated, if the derivative is negative on the interval itself. Yeah. Okay, so these are the two formulations of increasing and decreasing right here. Okay, and so now after we have put together that formulation on in terms of finding increasing and decreasing, it becomes a method, it becomes a technique for us to be able to detect those intervals that are increasing and decreasing actually. Okay, and so I have to re-emphasize again, and so before I head out to one example, let's really one more time look at the graph I had here on my board. But you see, increasing and decreasing now is a nature, is a feature that only happens in that interval between any two critical values, any two consecutive critical values. Okay, and so as I just said, it heavily relates to the critical values, because once we found the critical values, then automatically our entire line of real numbers will be split into separate intervals, and each one of those intervals will have either being decreasing or increasing. And so in that way, getting ready into our actual example, then we will have a clear planning of how to find increasing and decreasing intervals here. And so now allow me to introduce example 2. All right, so here we're at example 2 here. How about, let's say, find all interval or intervals, okay, of increasing, and also all intervals or intervals of decreasing. All right, so I want to find all intervals of increasing and decreasing. I mean, it could be more than one intervals for increasing, and there could also be more than one intervals for decreasing. Okay, and so that's the work we're about to get into. All right, so we're now at our part A of example 2 here. So now in part A, I am looking at this following function. F of x equals 2x cubed minus 3x squared minus 12x and plus 1. Okay, so if anyone who has been watching this video lesson closely enough, then all of a sudden you realize this example is exactly, this function itself exactly came out from the example 1, part A as well. Now, so my plan here is simply because I want to reuse a thing that we already have found in on the same function, but in example 1. And so now here in our work to find the intervals of increasing and decreasing, then yes, we have to find the critical values as I have explained through the graphs like that. But now we already found the critical values through our example 1. So here I'm just going to repeat that. So x equals 2 is one of our critical values, and we also found another one. X equals negative 1 is our other critical value for this function. And of course, it's also good to remind yourself that our derivative of this function, even though we already found all of this back in example 1, part A as well. So our derivative here is 6x squared minus 6x and minus 12. And so that is our derivative for this particular function right here. And we found two critical values. And so in order to find the intervals of increasing and decreasing, this is the first time I'm introducing a technique that's so-called, it's a sign chart technique right here. So what we are about to do here is we are going to construct a sign chart. Okay, we are going to construct a sign chart. And so the whole idea is about this. Think about the entire line of all real values, or just the x-axis itself. So the entire line of real values. So so now, back at the critical values. So now if we are going to take these two critical values and arrange them on our line of numbers in the increasing order, and that's because that's the way how it is. So now if we're going to take our two critical values and arrange them on this line, as I said earlier, then it makes sense that -1 comes before 2 on the line of numbers. And I think it's better that I'm going to write these values above the line here. So -1 is here and 2 is here. But so now once we have found, and just like how I demonstrated through the graphical illustration earlier, then once we place down the critical values, then automatically it's just the way it is. Then our entire line of real numbers here is being divided, being split it into, in this case, 3 separate zones, 3 separate intervals. And so now this interval here, the very first interval is the interval for any of those values of x being less than -1. Okay, and then this interval in the middle here is indicating those x values that are less than 2 and greater than -1. And this last interval here is the interval of those values of x greater than 2. Okay, and so now we realize we have 3 separate intervals, and again, this is just simply think of that as the line of all real values, and these are our critical values. And I am going to make them a little bigger size right here. Okay, so these are our critical values. Okay, so now the whole idea of the sign chart now is that I am going to construct, so right below this line I am to construct, and getting it into a table format right here, I am going to construct a row. Okay, but in this row I am going to investigate and check the sign. Now hear my words carefully. I am going to investigate or check the sign of my f prime of x. Okay, so the sign of my f prime of x, meaning, the plan here is that what is the sign of our f prime of x, or our derivative of x, derivative of f of x, when x is in this interval anywhere less than -1. And that's what the plan is. So here's the way. The easiest method, and it works anywhere, is as following. You already had your f prime of x calculated to be 6x squared minus 6x minus 12. Recall that. And so to check the sign of your f prime of x in this interval, all you do here is simply pick a value. And so I am going to pick a value. So the value I'm about to pick, let's say, and this is a value, as I said, this is a value that I picked. So you can pick a different value as well. But let's say pick a value in this interval for x. We can pick, how about x equals -2. Okay, sure negative 2 is less than negative 1. So this value we picked is completely good. What I'm going to do with this value that we picked, I am going to substitute that into this particular f prime function. So not the original function. Trust me, eventually somebody is going to mistake this, but now I have to, spell it out really clear. But we are going to pick a value in this interval, in this first interval, and we are going to substitute that value chosen into our f prime of x, meaning now I am going to evaluate f prime at negative 2. Okay, so I am going to take a minute to do the calculation. All right, so my calculation showed 24. But more importantly, this is what I'm looking at. The value is not important. This value was a positive value. And the reason I wrote that in red ink, because this is what we are aiming for. This is what we are aiming for. So that tells me that, so now I challenge you. You can try a different value for x as long as it's your x value that you chose stay in this interval. Then it's going to agree with my result here. My final sign of f prime of x in this interval is a positive sign in the entire interval. And this interval is for any x value less than negative 1. Okay, and that's the whole idea of what I so-called, I'm using a sign chart to check the sign of my f prime of x function, of my f prime of x as a function. Okay, so now once we're all clear with this first interval and successfully found our final sign of the f prime of x, then I am going to move on to the next interval. So in my next interval, again, my f prime of x, recall for yourself before we move on too far, 6x squared minus 6x minus 12. But now here we are going to pick a value of x that is in this interval anywhere between negative 1 and 2. Okay, and so now right now on top of my mind, I'm thinking of x equals 0. Because yes, x equals 0 that I chose stay completely inside of this interval between negative 1 and 2. And as I said again, when we were working with the earlier interval, this value I chose is only my choice. You can also pick a different value for x as long as your x value that you have chosen is inside of this interval anywhere between negative 1 and 2. So now I chose x equals 0. So what I am going to do, very similar to how I worked with the first interval here, I am going to take that chosen value, that selected value, and substitute that into this f prime function. Not the beginning, not the original function. So here I'm looking at f prime at 0. Okay, and so f prime at 0, and this is going to be an easy substitution. I don't think I even need to step away for the calculation. 6 times 0 squared minus 6 times 0 minus 12. All right, so my final value here comes out easily a negative 12. And again, I wrote that sign here being a negative 12, and I wrote the sign in red ink to indicate that really this sign right here, that final sign is what we are aiming at. So I could have also clarified earlier, even back in the earlier interval, or right now, for any viewers, for any of my students who are picking up a different value, you will end up with a different value here, but you will for sure get a negative sign. You will get a sign that agrees with my sign here. So now, what I'm saying is, in this interval for x value anywhere between negative 1 and 2, as we take a value like that, substitute into our f prime will be carrying out a final negative sign in that interval. So these are the sign values of your f prime. Okay, and so now, in this last interval of ours, so now as anyone starting to get engaged into this way right here, I can now start picking up pace a little bit. So now I am going to go. Feel free to pick your own choice and do your own independent calculation. I invite you to do so. So x equal, how about x equals 3? Okay, that's my choice. That's just my choice. I invite you to do this thing independently, and you should be able to come up with the same sign that agrees with me. So that means now I'm going to find f prime at 3, which into my f prime, it's going to be 6 times 3 squared minus 6 times 3, okay, minus 12. All right, and here I need to step away to do some quick calculation. My calculation turns out to be a 24 with a positive sign. So positive 24. So again, I emphasized positive sign right here, and that's what I need, because other students, other viewers who are picking up a different value here will end up with a different magnitude here, with a different value instead of 24. But I am sure you will be looking at a positive value if you do your calculation correctly. And so now that means in my interval here for x greater than 2, my f prime will be coming out with a positive sign final value, final output for my f prime. Okay, so now we just now have successfully checked the signs of all 3 different intervals, the signs of our final signs of our f prime of x on 3 separate different intervals. Okay, but now, and we are very close. We are very close in our work, because ultimately what we are looking for is, when we were looking for which intervals here is having a positive slope of tangent line, and that means a positive f prime. Which interval here has a negative slope of the tangent line, which is the positive final value of f prime. And so in that case, this chart right here is telling us, it's all about the story right there. And so now we can tell immediately that I am going to construct the final bottom row here as for the behavior of our original function. So now this bottom row is for the original function, sort of like we are about to put some conclusion of that. So now in this interval for x anywhere less than -1, our derivative of f, or our f prime, has positive sign for the output. That means that our function must be, our f of x function must be increasing. And that's exactly the formulation that we have learned. That's the formulation that we have learned just on the board earlier, right before we started getting into this example. Okay, and so now our function f of x here is increasing in that interval. And now in the next interval, the final sign of our f prime in this entire interval is a negative sign. So that's indicating, according to the formulation we have learned earlier, the general rule we have learned earlier, then the function itself here must be decreasing. Okay. The function must be decreasing in this interval. Okay. And for the last interval, of course, similar to the very first interval on the left here, then we are looking at another interval being increasing. And that's how I am applying our general understanding that I wrote down on the board earlier into solving a problem like this. And primarily this sign chart technique right here is an effective tool for us to track down all increasing and decreasing intervals. And so now, as far as tracking down and detecting all increasing and decreasing intervals, we're done. But let's just get back to our other board right there and finalize our final conclusion, our final answers. So, all right, so now I'm going to take some time to erase part of this work right here. So now, as far as increasing intervals, for increasing, then we have 2 intervals. Quickly, let's swing back at what we've seen earlier. We got 2 intervals that are increasing for f of x. And so those intervals are, one of them is anywhere from negative infinity to negative 1. Anywhere between, I should have said anywhere between negative infinity and negative 1. And the other one is anywhere between 2, positive 2, and positive infinity. Okay? But now in formal math, and since we're using interval notations right here, which is the most standard ones out there, so since we are using interval notations, then I am going to introduce this union symbol over here. It's indicating that if this union symbol, you might have seen that somewhere here and there in other math courses, but logically speaking, this means or here. Okay, that means if we are looking at the x values either in this interval or the other interval, then we are in one of these. Then we are having our function being increasing, and so that's what it says right here. We have two intervals: this interval or the other interval. Okay, so we found two intervals for increasing of our function, and so now for decreasing. All right, so we only found one interval for decreasing, and let's quickly look back at the other board where we were getting our sign charts constructed. So this interval anywhere between x values, containing x values anywhere between negative 1 and 2, that interval was a decreasing interval according to our work. So now concluding it, negative 1, comma 2 in interval notation, and that's the most, as I said, the most standard way and the most common way of expressing your final answer for these kind of problems, finding interval or intervals of increasing and decreasing. Get on example 1, back to example 1, but now part B. And so part B of our example, let's say we can just stay with this function. How about g of x equals cube root of x? And again, you can see that my plan here is that I want to reuse the work we have done for these functions from example 1 right here. So we're still in example 2, but now we want to find all intervals of increasing and decreasing. And so in that way, from past example, from example 1, and we have already found our list of critical values. As far as critical value, okay, we found that we've had x equals 0. It's not because our derivative here can be solved for equals 0, but x equals 0 gives us an undefined derivative. So hopefully that's you'll recall on that. So now we only have one critical value. Let's build the sign chart. Let's build a sign chart right here. Again, I'm going to spend a little time to construct again a different sign chart for this problem. So imagine the entire line of real numbers. Okay, but this time we only have one critical value. I am going to put it somewhere on the line of real numbers right here, and I call it 0. And so if this is 0 over here, where we call it, then it breaks our entire line of real numbers into two separate zones, two separate intervals. Okay, so this interval to the right-hand side is the interval for those values of x greater than 0. Okay, or in interval notation, 0 to positive infinity. That's another way of seeing it. Okay, and then this interval here, this zone here is the interval for those values of x less than 0, or being negative. There are a lot of ways you can understand that. Or in interval notations, minus infinity to 0. Okay, and so now I show you the easier technique, but works anywhere simply because see, here is a good example where the factoring doesn't work out too well right here, but we can save ourselves still. So I don't need all that fancy rows as in the earlier example, but now I can just make one row here directly for my f prime. And I'm going to eventually produce another row below for my f. So pick a value in this interval. I can make my own choice. You can make your own choice right there for the interval. So go with your own choice as well. But the point is, pick a value that's less than 0, a value for x that's less than 0. Okay, and so here I am. How about I'm going to choose for my work here? I'm going to choose how about -1. Okay, and recall for yourself. Quickly recall for yourself our g prime that we found from the earlier example, from example 1, that was 1 over, it's a cube root of x squared. Cube root, 1 over cube root of x squared. So that means if you pick -1, then substitute that in here, our g prime of -1. G prime, not g to the -1. G prime of -1 is 1 over cube roots, okay, of -1 squared. Okay. All right, so -1 being -1 in quantity square is going to force that to become positive, and taking cube root of a 1 is a 1. So 1 divided by 1 is a positive answer. And so here we're looking at our sign of the derivative here is positive for sure. And so now we have a positive sign that we just now found for our derivative in that first interval, and we only have 2 intervals, so we're almost done. But so that means in this interval our function must be increasing. Okay, so our function must be increasing. And then when it comes to the next interval, then once again I'm going to go g prime, I'm going to pick a value. Let's say x is greater than 0. Easy enough and naturally enough, people would pick 1. I'll pick 1 too. Okay, so when x equals 1, substitute it into our function. And I now just noticed that it should have been g the whole time. Okay, so here g prime at 1 is 1 over cube roots of 1 all squared. And with this value here, the final sign, I'm pretty sure the final sign will be positive again. Okay, after that overall calculation. And so now my function is increasing again. My function is increasing. Okay, and so now in that way, now we are ready for giving our final answer. So now for as far as increasing interval and decreasing interval, we don't have any decreasing interval, but we do have increasing interval. Okay, and so I gotta clarify this a little bit. It has become a controversy out there about this, and it's still a little bit hard to resolve. But for those students who are doing online assignments, then it's just some online assignment platforms can only, maybe that's the way they are. They only program to take your increasing intervals as 2 separate intervals. So, well, and that's right out from our chart right here. Then some web-based homework assignments, some platform for homework assignments can only accept as 2 separate intervals, -infinity to 0 in this case, and another separate one from 0 to positive infinity. So on some online assignments platform, then you might have to break it down into 2 intervals like this, because it came straight out from our table. But really, some web assignment platforms are actually smarter than this, because look at the way it is. Really, it's just 1 interval all the way from -infinity to infinity. Okay, so it's all about up to your tryout right here. It's hard for me to tell which platform can only go with this and which platform can be a little smarter. So it's all about, if you try this way, it doesn't work out, try the other way. In case like this, what I mean here is 2 consecutive intervals, but they're both doing the same behavior, either both increasing or both decreasing. So for us, the human being, we know for sure it's the same interval here, but on some web-based assignment platforms, it might be a little more picky that it's accepted as the separate intervals like this. Okay, so make your tryouts like that. Okay, but there are no decreasing intervals for this example. All right, and so now I am going to erase my board, and let's look into our part C of the example. All right, and again, I'm using that same function, the same corresponding function back in part C of our earlier example 1. So h of x here, e to the x plus e to the minus x. Okay. And so what I'm seeing here, again, we found the critical value, and the only critical value we found back in example 1 is x equals 0. Okay, and with something like this, it's like impossible to factor, and that's the reason why I introduced this easier method, but works anywhere for my viewer and for my students to be able to find effectively the sign of the derivative in your sign chart. So it's all about the sign chart techniques right here to detect interval of decreasing and increasing. So imagine once again on the line of real numbers, we're looking at x equals 0 is here. Okay, so that means this interval to the left is x is less than 0 or negative infinity to 0. That's one of it. And then for the other ones, it's x greater than 0 or the interval from 0 to positive infinity. Okay, and so from that point, once again here my function's name is h of x. So here I'm producing a row for h prime. I want to find the sign behavior of my derivative, and then the next row is for the function itself. Okay, so now we can pick a value. Think of -1. Okay, think of -1 here, and so -1 substituted into our h prime. And so recall for yourself that h prime was e to the x, but minus 1 over e to the x. Okay, so if we substitute -1 in here, my calculation came up with a negative value, and the actual value is pretty lengthy in decimal. So I'll just express the sign, and that's the more important part that we need. We need the sign of our derivative in this interval. Okay, and then again, now I'm going to pick a value, let's say +1. Okay, and then +1 being substituted into our, let's now spend some time calculating h prime at 1 right here. Okay, and so my calculation came out being a positive sign here. So that means our function is decreasing in this interval, and it is increasing on the interval from 0 to infinity. Okay, and so now as far as the answer, we found it right here, but we want to make a formal statement. And so as far as increasing, our function is increasing from from 0, anywhere between 0 and positive infinity. That's the interval we have for increasing. Okay, and as far as decreasing, okay, our function is decreasing in the interval anywhere from minus infinity to 0. Right. All right, and so now I have this FYT for everybody. All right, so with your function here being about f of x being 1/3 x cubed minus 5/2 x squared plus 6x. Okay, I want you to find all intervals of increasing and decreasing for this function right here. Okay, and then it's an FYT, so I am not going to step in with the steps right here. I'm only going to wait until you finish, and I'll be giving out the final answer. All right, so now hopefully you've had some answer. So those intervals. Okay, so as far as for increasing, okay, for increasing, we're looking at two intervals here. There's negative infinity to 2, or there's another interval being from 3 to positive infinity. Okay, so that's one of them. I mean, two intervals for the increasing, and then there's one interval for decreasing. From 2 to 3, between 2 and 3. That's the interval for decreasing.